can just stop.
Yes, Lynn, you're ready whenever.
Hello, everyone. I'm Lynn from MIT. My supervisors are Jenny and Jay from Melbourne Uni. So my topic is misinformation detection via transfer learning. I'm a third-year PhD student. So we got 3 stops here, 4 stops in total. We're gonna start from our background and the 3 research questions I have been working on. Let's get started. Misinformation and misinformation on social media. So the definitions of misinformation here we adopt is misinformation is incorrect or misleading information. And what happens on social media? We use our mobile phones every day. We check on the news and we say, we check on the presidential election about climate change or about COVID or vaccines. Yet all this kind of information is spreading on social media. And what we want to find out is whether this information is correct or not. So that's motivates us to do this research. And also about misinformation is like, if we say globally, all these countries every year are spending a lot of money on combat misinformation. So that's also another reason to motivate us to do this research. And the most accurate annotations for misinformation is the use manually to annotate the data. But if we think there is a large amount of data on social media platforms, what that's going to happen if we use like manual annotations is going to be pretty cost, and it's going to take a lot of time, and it's hard to keep up to date. So, and what happens on the, like if you use deep learning approach, we're going to need large amount of data to train the model. So there is approach transfer learning, and we what is transfer learning? Basically, we have a source task, and we use the source task to train the model 1, and we transfer the knowledge from the model 1 to model 2, and use the model to apply on the target task. That's what we mean by transfer learning in this case. And here is a pretty perfect taxonomy for transfer learning in NLP from Ruder thesis. So basically, transfer learning in this case in NLP can be separated into 2 types: transductive and inductive transfer learning. And if we apply in different domains, we call it domain adaptation. If we apply across different language, we call it cross-lingual learning. And for the inductive transfer learning, if the tasks are learned simultaneously, then we call it multitask learning. And if the tasks are learned sequentially, then we just say it's sequential transfer learning. So basically, this is what is the transfer learning in this case, and what is few shot learning in will be like the model can do the job without explicitly seeing the data before in the training process. And here comes our 3 research questions that we try to focus on. The first one is how to effectively detect rumors for an emergent event or in different language while transfer learning. And the second one we try to focus on is how to detect rumors, try to leverage both user and comment networks. The third one is how to detect state space sponsored trolls and identify different troll types while field shot learning. So let's move on to our first research question. We try to say, I got started with my PhD together at the same time with COVID. So I'm gonna put my first research question on the COVID. And the first part of the first research question will be like how to effectively detect rumors on Twitter for COVID-19, and what's the difference between rumors and non-rumors from topics and users and emotions. So for this piece of work, we try to basically do a binary classification to identify rumors and non-rumors. And the model we use is an ensemble model, try to combine the text-based and the user-based model. And we use labeled rumor data, Twitter 1516, Femi and semi-evil. That's the existing label data we have, and try to apply directly on the COVID-19 data and to say what's the classified rumors and non-rumors, what's the difference between these 2. And Here's the classified rumors and non-rumors cases. And from the topic analysis perspective, we identify 7 popular topics that has been discussed on Twitter during COVID-19. And we have found out the classified rumors have picked up some like popular hashtags like hashtag Bill Gates, hashtag 5G, and the non-rumors popular hashtags have like hashtag stay safe, stay home, stay safe about the lockdowns. And to the emotion analysis, we use a deep emoji. That's a pre-trained model with 63 predefined emojis in there. So basically you give it a piece of text, it's gonna predict the corresponding, like the most likely emojis based on the text input. And what we found out is like either in rumors and non-rumors source tweet, basically the angry red face is dominant. But for the replies, if we say like the top 3 replies are the same, and if we look at left part of the pie chart, we say that it's quite different. Like towards rumors, people are pretty angry, or like got the like devil face, angry face, sad face. But towards the non-rumors replies, we got happy, sing, love heart, all that. And if we also grab some popular hashtags for the rumors and non-rumors on the source tweet, and we saw that the red angry face pretty dominant on the hashtags we pick up. And for the non-rumors source tweet, we can see some like positive. We got pray, thumbs up, fighting. And if we look at the response, like on the towards rumors and non-rumors, we see the red angry face in all hashtags. But like for the non-rumors hashtags, we got like pray pretty dominant, and also some approval emojis like thumbs up and red love heart. So yeah, that's more while we're using the COVID data set, and then we found out there are more than like 1 language in the data. So we want to say like that's motivates us like how to effectively detect rumors in multiple language while zero-shot learning transfer. So we say that so that's got our second research question, how to do cross-lingual transfer to detect rumors. We come up with our framework. We call it cross-lingual transfer, and we got a data set in the source language, and we have a teacher model that is being like pre-trained language models such as BERT, and we got golden labels in the source language in the source data set. So the first step we use is we have the golden label, and we use it to fine-tune the teacher model. Once we have the teacher model fine-tuned, we got larger amount of posts in the target language that is unlabeled. So in that case, we use the teacher model to do a direct predict on the silver labels. Of course, the silver labels won't be like as accurate as the golden labels. So we like directly use that, and we use the filter and the balancing rule to filter out like the high quality or the most confidence data, the labels that is being generated. And we use that to train the student model. Student model is being initialized as a multilingual language models. So once the student model has been fine-tuned, it's going to replace the teacher model and to combine the golden labels in the source language. So we have a self-training loop in there to continue to tune the student model to let it pretty good, make it good at both language, both the source and target language. And finally, once the student model has been performed stable based on the validation data set, and then we use the test data, and we have the final predicted label. That's how we do the cross-lingual transfer. And we have done the test using Twitter 1516 and Weibo and the Femi data set. In this case, Weibo is the Chinese data set. So we will do, we have 4 different set of results. And we compare with supervised and zero-shot models. So first, let's say, if we initialize with the monolingual BERT, we plus the self-training loop, we can see there is a huge improvement there. And if we plus the self-training loop based on the multilingual BERT, and we can see it didn't perform good on the source language, but with the plus the golden labels plus the self-training loop. And we can say it's actually boost a lot and even surpass some supervised learning models. So what we're guessing for that happens, it might be like the different language in that case is like as a regularization to boost the performance on the source language. So what have we learned from research question 1 is basically there are like emotion difference, topic difference, and user difference towards rumors and non-rumors for the COVID-19. And for the zero-shot cross-lingual transfer, we propose a novel self-training loop to interactively refine the multilingual rumor detection model. And we also try to combine the ground truth labels in the self-training loop. So in that case, to boost the performance on the source language and also on the target language. So that's what we have learned from the research question 1. And let's move to the research question 2. In this research question, we try to figure out is on social media platforms, there are not only text, but also like users who interact with the source post. So we have the users, and we have the users who leave the comments, and also we have the user interactions. So we call it networks. And on the existing related works, there are like text-based approach, multitask approach, graph neural network approach. So, but what's the gap in there is like, there is no exactly a method that is try to combine the post and its replies and social relations of users to combine all those signals together to do the rumor detection. So what we try to figure out is whether we can combine all these two networks together, and how to like achieve the better performance, how to combine them, basically. So for example, we have someone post a source post on social media, and a couple minutes later, there will be someone to leave the comments or who either retweet the post, and a couple moments, the tree grew bigger, and we have the people leave the comments towards comments and repost the retweet of the retweet. So we can give the number to each node in the tree. And in this case, if we only grab the users who leave the comments, so we call it comment network. And in this case, we put in a tree structure. So, and how do we extract the knowledge, the signals from this tree structure is we pair the node with its direct parent. And in that case, we have a pair of sentence, and we give it to a bird or like either existing language models. And we let it to grab the representations for this pair of text and use that. In this case, we grab the CLS token and we use it as node representations for this graph. And we use graph attention neural network to combine to represent the graph structure. And once we have that, we go through our graph representation learning algorithm, and we generate our graph comment tree representations in this case. And let's go back to the original tree structure. In this case, we grab the users who leave the comments, but we put all the comments in a sequence way based on the time steps. And we call it comment chain. So what we do with the comment chain is we put it into a two-tier transformer. And in that case, we can say, we don't have the limitations on the number of tokens that's being restricted by if we only have one tier transformer, and we grab the representation through that way. If we go back again, what we're gonna have this time is we only care about the users who interact with the source post node 0. So in that case, we have a whole new tree, user tree here, and for each node, we try the different representations, and the more information we try to say, like we got node 4 and we got user 4 social following relationship in this case, to combine this into the node representations. And we use unsupervised graph auto encoder to encode the user social relationship. And then we use that to initialize the node, combined with the node, the user features in there. And then we still use graph attentional network to gather representations or from our user tree. So in that case, we have our duck that comes with the user tree, the comment chain, and comment tree. And once we get 3 representations, we simply concatenate them together and to do the final prediction. So that's how we try to combine all 3 signals and all the signals we have on the social media networks. And the data sets we use is Twitter 15 and 16, Code 8, and Weibo. So towards the result, we want to say, in the comment tree, does incorporating bird like, and from the results, we can say, we try different ways to learn the graph. And actually when we compare all of that, and when we do the comment chain with the 2-tier transformers, give us the best results. The user tree, when we combine the user social relationships, it gives us the best results. So yeah, that's all the doc, and got the source code up in the GitHub. And quickly finish the research question 3 is try to identify the state-sponsored trolls and identify different troll types. So in this time, we want to figure out the trolls on social media. So basically the internet users who intend to spread the misinformation and to provoke others into an emotion response. And our focus is on state-sponsored trolls, and we use Twitter data set. In that case, we care about who the users who spread the news on the social media. And yeah, that's why it has some political negative impact. So that's why to trigger us to do the troll detection. And then, oh yeah, let me finish this. Yeah, but based on the existing data set we have, from 2015 to 2016 and to 2017, and even like with time goes by, we have different troll activities on social media platforms. So, and for each different troll categories, it has its own target, and is related to a specific political event. So more trolls to come next year. And how should we detect them? And how should we use the limited data via few shot learning to detect them? So here is our proposed meta troll model architecture. We try to use few shot learning memo based on memo and try to detect the trolls with limited data we have. So yeah, that's the current work we are doing. That's it. Thanks.
Thanks. Yeah. I can take one question. So any question from the floor? Yep.
You're identifying trolls, but what about the paladins, the people that are actually introducing the good information, pointing to university research or whatever? You're finding those as well?
Currently, we only that should be non-trolls, right? Yeah, that's been classified as non-trolls we have. So basically, let me go back to the trolls. Here is what we try to say is, yeah, we didn't catch that kind of data in this research. Yeah, didn't specifically catch that. Yeah, yeah, all belong to the non-trolls, good people in this case.
Yeah, I just got a quick question. So you mentioned the first research is about the COVID-19 rumors detection on Twitter data, and I'm just curious about before you detect the rumors data, do you have specific definition about what is the definition between rumors data and the non-rumors data? So you analyze the different hashtag for the rumors data and the non-rumors data, but do you have some specific definition about it?
Okay, so basically the definitions what adopted in that case is rumors are while spreading informations that is unverified. So it can be true and it can be false and it can stay unverified, but it's while spread on the social media. That's rumors. So.
All right, then. Thank you so much for your presentation, Lynn. Another round of applause, please.